Not long ago, we learned about related rates. Related rates are problems that deal with finding a rate of change by relating it to other rates of change or other quantities, usually time. Related rates are also real-life applications of derivatives. Now let's do a simple example of a related rate problem. Let's say that there's a cylinder, this one, and its radius is increasing by 3 meters per second, while its height is increasing by 7 meters per second. What is the rate of change of its volume when its radius equals 5 meters and its height equals 3 meters? So the first thing that you need to do is to define what you need to find and write down what you already have. So you know that the rate of change of the radius with respect to time equals 3 meters per second, while the rate of change of its height with respect to time equals 7 meters per second. And its radius equals 5 meters and its height equals 3 meters at that particular instant. So what you need to find is the rate of change of the volume with respect to time. So how do you do this? Well, first you need to find an equation that relates all of these known values and this unknown value. So an easy equation would be the volume of the radius. So volume equals pi r squared times height. Now the next step is to derive both sides of the equation, leaving you with dv dt equals 2 pi r dr dt times height plus dh dt times pi r squared. And now you are left with an equation where you already know most of the things and you only need to find this one. So you plug in and what you get is dv dt equals 2 pi 5 times 3 times 3 plus 7 times pi 5 squared. And if you evaluate this, what you are left with and the answer of the problem is 265 pi meters cubed per second. So that is the rate of change of the volume of the cylinder at that exact particular instant when the radius equals 5 meters and the height equals 3 meters. Now let's try another example of a related rate, but this time it is an application of the semi-real world. Let's say that a meteor is flying towards Earth and it carries aliens that report that their linear speed is increasing at a rate of 250 meters per second. The angular acceleration of the meteor, because it is rotating, is 150 radians per second squared. And so what is the radius of the meteor if its rate of change is negative 15 meters per second at the time that the alien speed equals 600 meters per second? So first let's write down what we know. We know that their linear speed is increasing at a rate of 250 meters per second. So its linear acceleration equals 250 meters per second squared. And we know that the angular acceleration of the meteor is 150 radians per second squared. I don't know the symbol for angular acceleration, so dw dt will do. We also know that the rate of change of the radius of the meteor is negative 15 meters per second. And the alien's linear speed is 600 meters per second. So now we write the equation that relates all these variables. So angular speed equals velocity over radius. So now we derive, we find that dw dt equals dv dt, or let's just write this as r minus dr dt v over r squared. So now we just plug in. We know that the angular acceleration is 150 We know that the acceleration is 250. The radius is the unknown. And the rate of change of the radius is negative 15 meters per second. And the linear velocity is 600 over r squared. So simplifying this, and we get a quadratic equation where you get that negative 150 r squared plus 250 r plus 9,000 equals 0. So factoring this and solving for the radius gives that the radius at that particular instant equals 8.624 meters. This information would be useful for scientists to know, for example, I don't know, it would be useful for scientists. They know how to use lots of data. I figured out how this data would be useful. Let's say that scientists figure out that when the meteor, at the instant the meteor crashes with Earth, all this data applies. So if they want to know how big the crater will be, they need the radius of the meteor. So yeah, that's how they will use it. Another example of a related rate problem, and this one is a little bit more realistic, is when a machine gunner in World War II is shooting a plane that is 1,000 meters from the ground, and it remains at that constant height. The plane is moving towards the machine gunner at negative 150 meters per second. So how fast is his shooting angle changing if the plane is 400 meters from him? So again, first we write what we know. We know that the speed of the plane equals negative 150 meters per second. And we know that the plane is 400 meters from him. And we know that the height is 1,000 meters. And we need to find the derivative of the angle with respect to time. So the equation that relates all these variables together is theta equals arctangent of 1,000 over x. So to find the rate of change of the angle with respect to time, we derive both sides of the equation, leaving us with d theta dt equals negative 1 over 1 plus 1,000 over x squared times negative 1,000 dx dt over 400 squared over x squared, but x equals 400. So if we substitute all our values in and we solve for d theta dt, we get that d theta dt is 0.1293 approximately radians per second. So his shooting angle is changing at the rate of 0.1293 radians per second.